Alright, good afternoon everybody. So welcome back to CSE215. So we had a long break there because of a Monday holiday, but we're good until February, and then we got another Monday holiday in February. So this is effectively a 9-week course because we lose 4 hours of lecture. But there's always wiggle room in the topics and places to fit extra things in, so we'll be fine time-wise. So my goal for today is to dig deeper into propositional logic, talk a little more about quantifiers, universal quantifier, existential quantifier, and then start digging into rules of inference, which will really be the foundation for the formal proofs that we're going to do. And that's a main part of your next homework assignment, which is posted on Canvas. So before we jump into that, any questions to start with?
Why is your screen green?
Because I'm chowing down on ice cream. When I'm done with that, I'll open my camera.
Okay, that's long okay.
Yeah, it's my power lunch.
You know, on the last homework, there is question, let's see here, 3.3, question 2 had questions, what was it, parts C and D, I think, were on to write a proposition that implies X, and I had like zero idea how to do that.
Okay.
So I just couldn't do it, but I was wondering if you could explain how to do that.
So this was which question? 3.3, question 2.
Question 2, C and D.
Yeah. So let's see. We're given a proposition X. So let me just jot this down here, and then I'll move things out of the way. X equals P and not Q, or R and P. And so part C says, give an example of a proposition that implies X. So find a proposition, let's call it A for answer, such that A implies X. So what could such a proposition be? Certainly X implies X, but it says, find a proposition other than X. But what other proposition could we write so that A implies X is true? So any ideas from anyone?
The answer I would give for that one was just P. If P, then X.
So let's see where this gets us. If P is true, does that guarantee that X is true?
No, that's not what I wrote. Hold on.
Okay. Yeah, because P could be true, but if R is false and Q is true, then this X would not be true.
Okay, I wrote the expression P and not Q.
Okay. Right? And this is absolutely a true statement, right? If P and not Q is true, we know that X is true. How do we know that? Because X is a disjunction of P and not Q with R and P. So if this is true...
Answer for part D.
Sorry?
I said P before, that was my answer for part D.
Okay. So yeah, if this is true, right, if P and not Q is true, then this is true, and so this disjunction is true, and so X is true. So this is a valid statement. P and not Q implies X. So P and not Q is an example of a proposition that implies X. So that's a good answer for C. R and P would also be a good answer for C. it turns out the moon is made of green cheese would also be a valid answer. Because, if false implies X, well, this is always true. Right? This is the funny thing about if-then statements. If the hypothesis is false, the implication is true. So you could have used a proposition like, my teacher is the Queen of England, or the moon is made of green cheese, and that would have also been a proposition that implies X. But this is, kind of a more interesting one, maybe. And then for part D, it's asking for a proposition that is implied by X. So we want to find some other answer. Let me call it D for part D. So find a proposition D such that X implies D. So if you know that X is true, is there some other proposition we know is true? Clearly, if X is true, then X is true, but they want a proposition other than X. And so, yeah, if X is true, it turns out P has got to be true, right? Because if X is true, then either this is true, which means P is true and Q is false, or this is true, which means R is true and P is true. And so if you look at the truth table for this, you'll see that anytime X is true, P is also true. And so the following is a valid statement. X implies the simple proposition P. And so P would be a good answer for that question.
Okay, that makes sense. Thank you.
All right, was that a question?
That was, sorry.
Okay, cool.
Another question. If false implies X, X isn't always true, but false implying X says that X is always true?
No, this never says that X is true.
Is always true. Okay.
Yeah, this implication is true, but since the hypothesis is false, this says nothing about whether X itself is true or false. That's a funny kind of edge case, and it comes from this truth table. Right, so the implication is always true, except when the hypothesis is true and the conclusion fails to be true. That's the only time the if-then is false. All right, other questions? All right, while I play with my color settings. So, we're obviously still online today, and as I posted in Canvas, I'm just going to stay online until further notice. If numbers improve and it seems like it's going to be safe to go back in person, I'll post a notice ahead of time and we'll go ahead and do that. And for people who end up not being comfortable with that, you'll be able to, hopefully follow along with the videos and stuff. But until it's pretty clear to me that it's safe to go back, I'm going to err on the side of caution. And maybe it's safe right now, but with the data I have and the experiences I'm seeing of people around me, it feels like it's safer to err on the side of caution right now. So we're staying remote until further notice. But hopefully we'll get back to the classroom at some point. Alright, so I posted your next homework on Canvas, and it should make more sense after today's lecture, because it's mainly looking at formal proofs related to rules of inference. So we'll be talking about that in a little bit, but let's finish up our discussion of quantifiers. And so remember, we had two kinds of quantifiers. There was this upside down A, which means for all x, and there's the backwards E, which means there exists an x, and this is at least one x. There's also a backwards E with an exclamation mark, which says there exists a unique x. So exactly one x. But the usual existential quantifier says there's at least one x, but there could be more than one. This stronger version with the exclamation mark says there's exactly one x. And so we can think of this as applying to typically a family of propositions. So, you know, let P of n, where n is bigger than or equal to 0, be the proposition, you know, n squared
Sorry,
is...
I missed what the unique meant.
E with an exclamation mark means there exists a unique x.
But what does unique mean?
One and only one. So this says, you know, there is at least one x for which some statement following this is true. This says there's exactly one x for which some following statement is true.
Thank you.
Mm-hmm. So let P of n be the proposition that n squared is bigger than or equal to n. Right? And let's suppose that n comes from the set of integers. So in this case, P of 0 is the proposition that 0 squared is bigger than or equal to 0. And that's true. And P of 1 is the proposition that 1 squared is bigger than or equal to 1, and that's true. And P of 2 is the proposition that 2 squared is bigger than or equal to 2, and that's false. And P of 3 is the proposition that 3 squared is bigger than or equal to 3, and that's false. And most of these other propositions are false. Right? So we could say, you know, there exists an x such that P of x. This is a proposition, and this proposition is true because there does exist at least one x for which P of x is true. This says there is a unique x for which P of x is true, and that is another proposition, and that proposition is false because there's actually two x's for which P of x is true. This is a third proposition for all x, P of x. It says P of every value x is true, and that proposition is false. But the thing that's hard to keep in mind sometimes is that, you know, this whole thing, P of x is a proposition for any given x, right? Each P of x is a proposition. This is a proposition. That's a proposition. That's a proposition. This whole thing, there exists an x such that P of x, is another proposition. It's making a statement about what we find if we look at all of these propositions. And we can do some calculus on these quantifiers if we like. So let P of x be some family of propositions. And we need to specify, you know, what the range of x is. Does x, you know, range over all integers, positive integers, real numbers, prime numbers, odd numbers, people's names that contain the letter J? I mean, we've got to define what the universe is for this. But supposing that P of X is a family of propositions, we can write, for all X, P of X. And we can also write there exists an X such that not P of X. And it turns out that these are the opposite of each other. This statement says for any X you think of, P is true. If you put a negation in the front, this means there's some X where P is not true. And that's exactly what this says. There is some X such that not P of X is true. In other words, P of X is false. And conversely, this says there exists an X such that not P of X is true. There exists an X such that P of X is false, which means it's not true that for all X, P of X is true. So these two statements are equivalent. And this may feel a little De Morganish to you. We can negate this side by changing the for all into an exists and negating the thing on that side of the quantifier. Similarly, if we say there exists an X such that P of X, well, if we negate that, there does not exist an X such that P is true. That's equivalent to saying for all X, P is false. So those two statements are equivalent. And we can kind of see why this is believable. By thinking of the following. So suppose we write something like, for all X contained in the natural. So I'm going to use the natural numbers to be the set 0, 1, 2, 3, and so on. So non-negative integers. Suppose we say for all X, P of X. Well, what we're saying is, if I set X equal to 0, which is a natural number, P of 0 is true. If I set X equal to 1, P of 1 is true. If I set it equal to 2, P of 2 is true. And so to say for all X, P of X is true, this is equivalent to saying P of 0 is true, and P of 1 is true, and P of 2 is true, and so on and so on. On the other hand, if I say there exists an X in the set of natural numbers such that P of X, I don't know if P of 0 is true. I don't know if P of 1 is true or P of 2 is true, but I am saying that there is some number X such that P of X is true. And so this is actually equivalent to saying P of 0 is true, or P of 1 is true, or P of 2 is true, or etc., etc. And so there's a connection between these quantifiers and conjunctions and disjunctions. And if you use these equivalences, then these statements really are just De Morgan's theorem. This is the negation of a bunch of conjunctions. That should give you the same thing as a disjunction of a bunch of negations, which is the existential quantifier applied to not P of X, and so on. And this is fun stuff because it's taking things that's make some sense intuitively, right? If it's not the case that all of these is true, there must be at least one that's false, right? Which means there exists an X such that this is false, right? P is false, not P is true. It's taking these things that you know, can make some sense intuitively and giving us the machinery to treat them very formally, right? And to use things like, you know, De Morgan's theorem from Engineering 250 and ands and ors and so on to add some certainty to our intuition, right? Which is the whole power of this idea of propositional logic. All right, so let's just dig a little deeper into that. So what about for all x, p of x, and q of x? For all x, p of x and q of x is a true statement. That's what this proposition says. Well, this is the same thing as this. This is the same thing as saying for all x, p of x is true, and also for all x, q of x is true. Right? If any x that you think of makes this conjunction true, then for that x that you thought of, p of x must be true, which means this is true. And for that x you thought of, q of x must be true, which means this is true. So this certainly implies that. And if this is true and that's true, then for any x you think of, p will be true, and since this is true for all x, q will be true for that also, and so p and q will be true for that x. And so this implies that. So these are logically equivalent. How about these? Are these logically equivalent or not?
I think so. Because, yeah, either p of x is true or a of x is true for all i's of x.
So I mean,
Yeah, that's exactly the same.
it looks reasonable, and from symmetry, it seems like the same thing, but you don't think they are. You got a counterexample?
No, I don't have an example, but trying to think here.
So let's work over the family of integers. And let p of x be the proposition x is even. Let q of x be the proposition x is odd. So for any x, x is even or x is odd. That is true, right? So for all x, this statement is true. But this statement says for all x, x is even. That's false. This says for all x, x is odd. That's false. So this disjunction is false. So this is false, but this is true. So these are actually not equivalent.
Okay, interesting.
Yeah, that's pretty subtle. And there's a dual to this. Right, there exists an x such that p of x or q of x. There exists an x such that p of x, or there exists an x such that q of x. And so for this to be true, right, for every x, one of these has to be true. Which means that if so there has to be an x where at least one of these is true. Well, if there's an x where p is true, then this statement is true. And if there's an x where q is true, then this statement is true. And so this will certainly be true. So this implies that. And if we know that there's either an x where p is true or where q is true, then for that value of x, p of x or q of x will be true, and so there will exist an x where this is true. So this implies that, so those are equivalent. And then, as you might expect, this will turn out to not be equivalent to this. This says there exists an x where both p and q are true. This says there exists an x where p is true and there exists an x where q is true. Let's see, are those really not equivalent? If they're equivalent, I'm done. It's an x where p is true and q is true. So we could use the same propositions here, right? This says there exists an x such that x is even. Well, that's certainly true. 0. This says there exists an x where x is odd. Well, that's certainly true. 1. So this statement is true, but there does not exist an x where x is even and x is odd. So this side is false. So they're not equivalent. And remember, this x is just a placeholder, right? This is not saying that whatever x makes this true has to be the same x that makes this true. Right? This proposition says there is a number that is even. That's a true proposition. That's all it says. This proposition says there is a number that is odd. That's all it says. Nothing in here says there's a number in here that is odd, and that number has to be the same x that I used to verify that this proposition was true. Right? But over here, I'm saying, there is a single x such that that number x is even and that number x is odd. Right? That's the difference. So these are in some sense, simple thinking about the definition, but they get really deep really fast. Right? If you start thinking about this deeper and deeper, you can get into some really kind of heady stuff. About what the difference is between these and ways of thinking about cause and effect and stuff like that. All right, so last thing in this area is nested quantifiers, and these can look confusing, but there's a way we can break these down, and it's similar to dealing with nested summation symbols. So let's suppose x and y are integers for all of this, so I don't have to keep writing it. So here's a statement: for all x, there exists a y such that x plus y equals 0. Right? This is a proposition that has two propositional variables in it. It's a proposition for any x and y I pick. This is a different proposition. If x is 5 and y is 10, this is the proposition that 5 plus 10 equals 0. Happens to be false. If x is 1 and y is negative 1, this is the proposition that 1 plus negative 1 equals 0. Happens to be true. Right? But we want to make this shift from just looking at this and immediately thinking about algebra to seeing these things as propositions. Right? Declarative statements that have a truth value. So this is a proposition that says something about x and y. It says that x plus y is equal to 0. All right, this is a proposition that says there exists a y such that x plus y is equal to 0. This is like, you know, a new proposition, P of x is the proposition there exists a y such that x plus y equals 0. So P of 0 is the proposition there exists a y such that 0 plus y equals 0. P of 1 is the proposition there exists a y such that 1 plus y equals 0. So P of 5 is the proposition there exists a y such that 5 plus y equals 0. Right? This is a family of propositions. All right? So we can write down what each of these propositions means. We could write down what P of 0 is, P of 1, P of 5, P of negative 10, P of 13 billion. Right? Each of those is a proposition. This is the proposition that for all x, this proposition is true. So this basically says P of 0 is true, P of 1 is true, P of 2 is true, P of negative 1 is true, P of 18 is true. It says that P of x is always true no matter what x is. Well, what is P of x? It's the proposition that there exists a y such that x plus y equals 0. So is P of 5 true or false?
True.
It's true.
True.
Because, you know, negative 5, if y happens to be minus 5, 5 plus y is equal to 0. And P of, 100 is the proposition that there exists a y such that 100 plus y equals 0. Is that true?
Yes.
Right? And P of, negative whatever is also true. And so it turns out that for all x, P of x is true. So this proposition here is true. And you can get there by, first taking this inner piece and just thinking of that as a proposition. And think about what that proposition says. And maybe look at it for some particular values and get a feel for it. Does it seem like it's always true, sometimes true, never true, true in one case, and so on? And then just rewrite this as, for all x, P of x. And think about that. And this is like with nested summations. We said just treat the inner summation first, turn that into some kind of formula, and then just take that sum using the outer summation. What about this one? There exists an x such that for all y, x plus y equals 0.
Yes. True.
True?
Yeah, because if y is positive for x, or if y is positive, x can be its negative equivalent, and vice versa.
Okay. So let's do the same thing. Let's make this a proposition called P of x. So P of x says for all y, x plus y equals 0. So P of 1 says for all y, 1 plus y equals 0. P of 2 says for all y, 2 plus y equals 0. P of, 18 says for all y, 18 plus y equals 0. So let's look at the truth value of each of these. For all y, 1 plus y equals 0. Is that true or false?
False.
Yeah, that's definitely false. And for all y, 2 plus y equals 0. That's not true for y equals, 15. And for all y, 18 plus y equals 0. That's false. And in fact, whatever value we pick for x, P of x is always false. So does there exist an x such that P of x is true? No. So this proposition turns out to be false.
I was looking at the, I don't know what you call them.
Yeah. So that's just the way I pick these propositions, and I pick them deliberately to be, confusing like that. Now there could be, a proposition family here for which this is true and this is true, or they're both false, or this is false and this is true, right? So they're definitely not equivalent. Changing the order of those quantifiers sometimes gets you different things. And you can nest these a lot of different ways. So there exists an x such that there exists a y such that x plus y equals 0. Well, that's definitely true, right? X equals 0, y equals 0 is one example. For all x, for all y, x plus y equals 0, that's certainly false. Because, x equals 1, y equals 2, this proposition is false. And so on. All right, good enough on that. So there's some homework questions on that, and they take some thinking about. But the main takeaway from this is these things don't always work the way that they might feel they should work intuitively. But you don't need to rely on intuition, right? Break it down into sub-pieces and work forward from there until you get to the whole proposition. All right, so we're going to kind of leave all of that in some sense and come into the next major part of this course, which is rules of inference. And this is the foundation for what's going to become our way of doing formal proofs. And formal proofs will be something we come back to again and again. We went through a kind of rough example last week of a proof using some identities and laws of logic. But we're going to formalize that further this week. And here's the main idea of rules of inference. We're going to do some examples like this. If it's sunny, then I go for a run. That's a proposition. It happens to be an if-then. But it's a proposition. It's making a declaration. It has a truth value. And we don't know whether this is true or not, right? Unless you're spying on me. We don't know if this is actually a true statement. It is a proposition, but it could be true, it could be false. I'll give you a hint, it's false lately. But, it could be true, it could be false. All right, here's another proposition. It is sunny. Could be true, could be false. Looks like it's false. But another day it might be true. Here's a third proposition. I go for a run. Or I'm going for a run, if we want to be plain English, right? And that could be true, that could be false. Okay, we're not making any claim about the truth or falseness of any of these three propositions. And we probably have no way of knowing whether those propositions are true or false. That's a question of knowing my internal algorithm and observing the weather and, monitoring my activities. And we probably don't know whether these things are true or false. But even without knowing that, we do know one thing. We know that if this proposition is true, and this proposition is also true, then we know this proposition is true. So let me put this in that's a specific example. Let me put it in a general form. Suppose we know that this is true, and we also know that P is true. Then we can conclude without any doubt that Q is true. And so we can read this as follows. If this is true, and P is true, then Q is true. And again, subtle but important point. We're not saying that I'm going for a run. We're not saying that it's sunny. We're not even saying that if it's sunny, I'll go for a run. All that we're saying when we write this is that if this is a true statement, and this is also a true statement, then you're guaranteed this is a true statement. In other words, we can conclude this from these two statements as long as we know those two statements are true. And that's all we ever do with these rules of inference. Right? We don't actually prove that it's sunny out. We don't prove that I run every time it's sunny out. All we can prove is that, if this is true and this is true, then this is true. And so we're going to do a lot of proofs, right? If n is an even number, then n squared is also even. Well, we don't know if n's even. N could be 17, But if n is even, then n squared is even. We're going to prove that. If P implies Q is true and P is also true, then Q has got to be true. Now, a different way to write this, that's closer to what we've been doing, but is a lot more cumbersome, would be this. P implies Q and P. If both of those are true, then Q is true. But this is a different version of writing this. And when we do this, this is how we're going to make our formal proofs, right? We're going to list a series of propositions, and the idea is everything above this horizontal line is true. Either because we're assuming it's true or we've shown that it's true. And the way you read this whole thing, this is a proof, the way you read this whole proof is if all these things above the line are true, then the thing below the line is true. So this is like a then or a therefore. And there's different ways of writing this. So there's notation here. And I mentioned this in the notes on Canvas related to the homework that just got posted yesterday. Another way of writing this is with commas. P arrow Q, comma P implies Q. The comma is taken to mean conjunction. Given this and that, we can conclude Q. And to avoid the arrows getting confused, a lot of times what you'll see is something like this. You'll see a double arrow. And the double arrow means all the stuff to the left taken together implies the thing to the right. And so you might see parentheses around things like this. You might see parentheses around the whole thing, or you might not see any parentheses. And you need to know that this double arrow is not saying, P implies Q, right? It's saying, given that P implies Q and given P, those two things together imply Q. So some of the questions in the homework use this kind of notation. And like I say, I put a note in the assignment on Canvas that says, hey, here's what this means, right? But when we write these proofs ourselves, we'll generally stick to this notation where we list, each thing on a separate line one below the other, and then eventually draw a line, which means therefore, and the thing below the line is what follows from all of these things. Alright, so these are the rules of inference. And you can find these in the textbook, and it's on page 58 and 59. 58 is the basic logical laws. We looked at those last time. So page 59, these are the rules of inference, or common implications. Detachment, indirect reasoning, disjunctive addition, conjunctive simplification. These are fun things to say in front of friends to impress them. Biconditional equivalence, contrapositive, right? Each of these is a theorem, right? And these are written out in this horizontal form, but we're going to write these in this vertical form that we used. So let's start with this first one, detachment. P arrow Q and P implies Q. So that's the thing we've already written. P arrow Q, P, therefore Q. That's detachment. And it's really just an if-then. This says if P, then Q. This says P. Well, if P is true, and if P, then Q is true, then Q must be true. Bang, there we go. If you're guaranteed that if it's sunny, I'm going to go for a run, and you know that it's sunny, I'm going to go for a run. There's no choice. Logic doesn't leave room for a choice in that situation. So that's detachment, sometimes called direct reasoning. Here's something similar. It's called indirect reasoning. P arrow Q and not Q implies not P. So given if P, then Q, and also given not Q, we can conclude not P. That's indirect reasoning. All right, what's going on here? If it is sunny, then I'm going for a run. And by the way, I'm not going for a run. If both of those are true statements, your only possible conclusion is it's not sunny. Because if it was sunny, I'd be going for a run, but I'm not going for a run. So it cannot be sunny, so it must not be sunny. So that's indirect reasoning, and that's really just the contrapositive. And in some ways, it's equivalent to detachment, but sometimes it's easier to think of this rule of logic when we're trying to come up with a next step for a proof. All right, disjunctive addition. P implies P or Q. So that looks something like this. Given P, we can conclude P or Q. And the value of Q makes no difference. Q could be the proposition that, the Earth has rings around it, right? Q could be the proposition that, I don't know, fish like to walk around downtown, right?
For all the Matrix.
Yeah. All that this is saying is if P is true, then P or Q is true. So, maybe P is the proposition that it's raining. If it's raining, then it's raining, or fish like to walk around downtown. This is logically correct. Because if P is true, this statement is true, no matter what Q is. Doesn't matter if Q is true or false. If P is true, then P or Q is true. So this is really just kind of, the notion of what a disjunction is, an or statement. There's a similar version to this. If P and Q is true, then P is true. And that's conjunctive simplification. If P is true and Q is true, P is true. How do I know? Because I just said P is true and Q is true. So P must be true. And there's another version, if P and Q is true, then Q is true. So you
Do
get...
we need to memorize these, or can we use these on our cheat sheet?
You can definitely put you can put anything you want on your cheat sheet. So yeah, you can definitely use these, and I would just write them down in some succinct form. But chances are you're going to remember most of these by the time you get to the midterm, because you're going to use these a lot in homeworks, and we'll use them a lot in class. But yeah, you can definitely put them on your cheat sheet. So P and Q implies P, P and Q implies Q. Disjunctive simplification, P or Q and not P implies Q. This one's really powerful. P and Q, sorry, P or Q, not P, implies Q. So that's disjunctive simplification. What does this mean? This statement says either P is true or Q is true. It says at least one of them has to be true. This says P is not true. Well, if P is not true and one of these has to be true, Q must be true. And so that's a nice way to prove Q sometimes, by knowing something about P. So that's disjunctive simplification, and that works in two cases also. All right, chain rule is the funnest of them all. Suppose that P implies Q, and suppose Q implies R, then P implies R. That's the chain rule. And it's a lot easier than the calculus chain rule. It's transitivity, basically, right? This says if P is true, then Q is true. This says if Q is true, then R is true. So if P is true, what do we know? If P is true, Q is true, and that means R is true. So P implies R. That's the chain rule. And then conditional equivalence, which I don't think is strictly necessary, but sometimes it's useful. And this is one of these things where for some people, this makes more sense than some of the other rules. So conditional equivalence says if P then Q is equivalent to, and they use the two-headed arrow with two bars on it for conditional equivalence. I use the 3 equals sign. They mean the same thing. So P implies Q is logically equivalent to not P or Q. How do we know that? Make a truth table. And do a sum of products. I said it. Engineering 250. Sum of products, right? So everywhere that we have a 1 in the output value, let's write down the min term corresponding to this. P bar Q bar, or P bar Q, or PQ. Should we do a K-map? We won't do a K-map. But we could do a K-map which would compress these two in a single term. P bar Q bar or P bar Q. This turns out to just be P bar. Yeah, let's do a K-map. It's been a year. So here's P, here's Q, and these are going to be 1 everywhere except where P is true and Q is false. So we're going to get a set of blocks like that. So what is this? This is P bar, and Q doesn't matter. And this is Q, and P doesn't matter. And so this condition is equivalent to P bar or Q. which, if we write it in the language of propositional logic, is not P, disjunction Q. So from a truth table, we can see this equivalence, and we get to pull out our 250 neurons and flex those. And biconditional equivalence, same thing, right? It's saying that P if and only if Q is the same as if P then Q and if Q then P. It's also the same as P and Q or not P and not Q. And if you look at the truth table for biconditional equivalence, it's true, false, false, true. And these are just looking at, you know, those truth table values and coming up with equivalent expressions. And then contrapositive, we've already talked about. If P then Q is the same thing as if not Q then not P. Right? This is the contrapositive of that, and we already talked earlier to say that the contrapositive was equivalent to the original implication, whereas the converse and the inverse are not. So these last three equivalences are kind of different. The ones above here are all implications. All right, and why is this useful? I'll give you one example. There's the theorem. A and A implies B, and B implies C, and C implies D, and yada yada, and Y implies Z, taken all together implies Z. And we can prove this pretty easily using the chain rule. Right? A implies B, and B implies C. That tells us A implies C. And A implies C, and C implies D. Chain rule those together, we get A implies D. And after 25 iterations of this, we can prove from these 26 propositions that A implies Z. And we're also told that A is true, and with direct reasoning, detachment, we can conclude Z. So these things will give us Z. And it's, you know, fewer than 30 lines to prove that. To prove this with a truth table, we've got 26 variables. That's going to have 2 to the 26th rows. That's 64 million rows in our truth table. And it's going to have a bunch of columns in there, and that's a really big sheet of paper. So yeah, we can prove equivalences or implications or statements about propositions using truth tables, but sometimes that's a really cumbersome way to do it. Now, it's great for a computer, not so great for us. But we can use these rules of inference to prove statements like this with sometimes very few number of steps. All right, so let's take a short break. We'll come back in 5 minutes. And let's see, that will be 14:06. Come back in 5 minutes, and we'll start using these to do some proofs. it going?
Hi.
Hey, how's it going?
Good.
I'm on break for another 15 seconds. All right, welcome back. Any questions yet?
Just on lecture, you're saying?
Yeah.
No.
Okay.
I have a question.
Yeah.
What flavor of ice cream were you eating earlier?
I think it was like chocolate brownie chunk fudge something or another. It's a Tillamook.
Oh, no, I want some.
Yeah. It was good.
Vanilla ice cream with maple syrup. Only way to go.
Oh, nice. All right, so let's see an example of this, and I'm going to do an example first with a word problem, and then we'll dig into some other aspects of this. So let's look at a word problem here. I'm going to state a theorem, and then we're going to prove that it's true. So here's the setup. I'm going to say if you send me an email, then I'll finish my homework. So that's my first statement. If you don't send me an email, then I'll go to sleep early. If I go to sleep early, then I'll wake up happy. Therefore, if I don't finish my homework, I'll wake up happy. Alright, so I have three statements followed by a conclusion. And I want to know, is this true? Is this valid?
I don't think inherently it is, because
Going to sleep early doesn't necessarily mean you're not going to finish your homework.
Right.
yeah.
So this is, at best confusing, but let's tackle this with propositional logic. So we've done some homeworks where we had, compound propositions like this, and we created propositions for parts of this, and then used those to express the compound statements. So let's make some simpler propositions. So let me start off with let E be the proposition. You send me an email. And I'm doing that because, I've got that piece here and I've got that piece here. Let W be the proposition. I'll finish my homework. it's W for work, because I've got that in a few pieces of this. And let S be the proposition I'll go to sleep early. And now I'm going to rewrite these propositions using EW and S. So this first proposition says, if you send me an email, then I'll finish my homework. So it says E implies W. This second proposition says, if you don't send me an email, so that's negation E, then I'll go to sleep early. So I'll go to sleep early is sleep. The third proposition says, if I go to sleep early, then I'll wake up happy. And waking up happy, I didn't put down. So let H.
It would never happen.
Yeah, right? I always wake up happy. I'll wake up happy. So if I go to sleep early, I'll wake up happy. The conclusion, that we're not sure if it follows or not, is if I don't finish my homework, so not W, then I'll wake up happy. So now we can toss out all of the imperfect, imprecise English, and we have a simple theorem we're trying to prove, which says, E implies W, not E implies S, S implies H, therefore not W implies H. And we want to know if we can prove this from these things. Okay, so here's how we're always going to do this proof. Okay, when we want to prove something like this, we're going to start with the things that we know. We're going to use rules of inference to conclude other things, and we're going to keep doing this until we have proven this thing that we're trying to show. Alright, and that's all we can do. We just write down things that we know are true, and then from those and from rules of inference, we write down more things that we know are true. And if eventually we write this down, it means we know that's true and we're done. That's the end of our proof. So this is where we get into this kind of game playing mode, right? Where we have all of these things at our disposal, all of these different rules. And I can kind of move them off onto the side here. And the question is, what of these could we use to try to take the things that we know and come up with new things that we don't yet know? So are there any rules of inference in any of these propositions that we might be able to put together and come up with something new? Because right now we don't have anything that says not W implies H.
Not E implies H.
Okay, how do we get that?
Because not E implies S, and so therefore then S implies H.
Mm-hmm.
So it's what attachment? Attachment. Sorry, disjoint. No.
Yeah.
Chain rule. Thank
Good
you.
old chain rule. Awesome. All right. So how do we write that formally? So let's say we want to prove this. All right, that's what we want to prove. So let's begin. The first thing I'm going to do is I'm going to say not E implies S. And how do I know that this is true? Because this is a hypothesis. Remember, our goal is to prove that this and this and this taken together implies this. So when you want to prove, if P then Q, what you do is you assume P is true, that's the hypothesis, and you try to show that Q is true. That's what it means to say if P then Q. So to show that if these things are true, that thing's true, first we have to assume these things are true. So I write this statement, not E implies S. And everything I write here has to be true. How do I know that's true? Because it's a hypothesis. I'm assuming it's true. And I'm allowed to do that because that's the name of the game here. Assuming these are true, can I prove that conclusion? So that's a hypothesis. And I can write a second statement just as easily. I can say if S is true, then H is true. How do I know that? That's also a hypothesis. Alright, and now we can do what someone suggested. We can use a rule of inference. We can use a chain rule. Because this chain rule says, you know, if P implies Q and Q implies R, then P implies R. Well, that's our setup. Not E implies S, S implies H. We can conclude from that, not E implies H. But we got to justify it. I've just written something that's not a hypothesis. How do I know it's true? I know it's true because of something called the chain rule. And we want to help the person reading this proof to believe that this proof is true. So I'm not just going to say I use the chain rule. I'm going to say I use the chain rule to combine propositions 1 and 2. Well, I mean, those are the only propositions I have. But if I had 80 lines of proof, I could say, you know, look at lines 17 and 25 and use the chain rule. So now the reader's convinced, oh, okay, this is also true. All right, is there anything else that I can do?
You can use contrapositive on the first line. What was that? If E then W.
If E then W. So why do you want to use the contrapositive?
We're trying to find the relationship if not W then H.
Mm-hmm.
If you do the contrapositive on E, if E then W, then you'll end up with not W, then if not W, then not E.
Okay,
and,
cool.
Then we have this relationship not E, if not E, then H, and so it kind of would tie together with another chain rule.
Awesome. All right, so this is puzzle solving, right? There's no direct formula where you just, you know, follow these steps and at the end of it you've got a proof. You gotta try things, you gotta think about things different ways. Sometimes you just have to trial and error. But, you know, we just found a rule that uses not E, right? And we already used the not E here. There's only one other proposition that has an E in it. That's this first proposition. And we want not E. And after you've done enough of these, you'll start to think, hey, if I've got an E and I want not E, let's try contrapositive. Because contrapositive turns you from, you know, P into not P. And Q turns into not Q. And even if you don't know why this is going to help you, it might be something to try. And this is, you know, a good example of, you know, working in pencil, or working on a whiteboard, or having a lot of scrap paper available. Because sometimes it takes multiple attempts. You might try doing this, and you might try doing that, and then maybe the third thing you try gets you a little further, right? So let's just try that. Let's take the contrapositive of this first statement. Well, I can't do that until I've written down this statement as part of my proof. So step 4, I'm going to write if E, then W, and that's a hypothesis. And step 5, I'm going to take the contrapositive of this and say not W implies not E. And the reason is contrapositive. And again, I'm going to point out that I applied the contrapositive rule of inference to proposition 4. All right, and so now we got another chain rule opportunity. Not W implies not E implies S. Let's just chain those together. And we say not W implies S. And the reason for that is chain rule. And I used propositions 5 and 1. And now if you're reading this, you can say, oh, here's proposition 5, not W implies not E. Here's proposition 1, not E implies S. What's the chain rule say? Oh, it says I can put those together. I should get not W implies S, right? These justifications for each step let somebody reading this conclude that each statement you're writing is in fact true, either because it's a hypothesis you're assuming or because it follows using rules of inference and things that you've already shown are true.
Could we have just said that the chain rule from, what was it, 5 and 3?
5 and 3. Did I do the wrong chain rule? I did. Bogus. This is why you do it in pencil. So, not W implies not E, and not E implies H. So I can chain those together and say not W implies H. And that's the chain rule of 5 and 3. Well, that's a much better proposition to have written down. Why? Because that's what we're trying to prove. Right? We're trying to prove the thing below this therefore line. We're trying to prove not W implies H. We just proved it. We are done. But you got to let the person reading the proof know that you're done. So you do that by writing QED. And when you write QED, this means the prior proposition is what you were trying to show. And that's the end of your proof. So there's a very formal proof using propositional logic that these things imply that, which means that these statements imply that. So yeah, if I don't finish my homework, I'll wake up happy. Apparently. All right, questions about that?
So it is true then?
So it is true, yeah. And logically, right, if I don't finish my homework, it's gotta be the case that you did not send me an email. Because if you sent me an email, I would have finished my homework. So if I say I don't finish my homework, that's also saying you did not send me an email. And this says if you don't send me an email, I'll go to sleep early. And if I go to sleep early, I'll wake up happy. That's why I'll wake up happy if I don't finish my homework. And it's not necessarily something that feels quite right intuitively, and that's good. It's always cool when you can do this and you can prove something that may not seem like it should have been provable.
If we're being really strict about it, we would say, instead of saying if you don't send me an email, we would say not if you send me an email, right?
Right. So yeah, that's technically how we would interpret it. E is the proposition you send me an email, so this is not you send me an email. So if not you send me an email, then I will go to sleep early. So it's kind of Yoda speak. All right, other questions on this? And this is just practice, right? You've got a whole section of theorems to prove like this. There's some questions I think where you start with sentences, but mostly it's questions where you have things like this, and you want to work through them and reach the conclusion. So let's do one of these from the textbook. you've got some questions from 3.5. So let's do 3.5.3. Question E. And I'm going to write this down, and then I'll move my paper out of the way. So we're given not Q, we're given P implies Q, and we're given P or T, and we're told that this implies T. So we're looking at this one right here. So not Q, P implies Q, P or T implies T. Don't ever copy these down wrong, because you'll end up trying to prove something that's not true. So written in vertical form, not Q, P implies Q, P or T implies T. So any ideas how to prove this? Anything we want to try?
Start with contrapositive.
Okay, contrapositive on this one, I'm guessing,
Yeah, PQ.
because that's our only if then. All right, so first we have to write the proposition if P then Q. That's a hypothesis. And then take the contrapositive. Not Q implies not P. That's the contrapositive of step 1. That's a P. All right. Anybody else got an idea?
So what's the weird double? I'm sorry if I missed it, but
This?
the equal. Yeah.
It's a way of implying parentheses. It's really just a single arrow, but it has the added function of saying all the stuff over here taken together implies whatever's on the right. So you can think of it as just a single arrow with parentheses around all of this and parentheses around that. It's to keep, you know, arrows in here as from getting confused with this arrow, which says all of this implies that.
Okay.
And this is basically where that horizontal line is going to go, which means therefore.
I have another thought on where to go from here.
Mm-hmm.
So because not Q, I can't, or I'm not sure which rule this is, but because not Q, therefore not P, and if P or T is true, then T has to be true. Because I guess not P is true.
How do we know not P is true?
Because of the contrapositive.
Well, so this says if Q is if not Q is true, then not P is true, but that doesn't tell us that not P is true.
But not.
It does, because we already know that not Q is true.
Ah, okay. So we can combine this with another proposition, which is not Q, and then use detachment. So let's list all of those steps. First, we have to state that not Q is true, and that's true because it's a hypothesis. And then we can use detachment or direct reasoning and say, well, given this and this, we can conclude not P. So we get not P, and that's detachment, using propositions 2 and 3. And you're really just holding the reader by their hand, right? You're saying you don't have to really think too hard about this, just keep nodding your head. And you're handing them, you know, the exact reason why each of these things is true, right? Well, this is detachment of these two rules. Why is this true? Well, it's a hypothesis. How did we get this? Well, we used the contrapositive on this, which was a hypothesis. So you're absolving the reader of having to think, right? They have to be able to know what these rules mean and confirm that, you know, if you apply detachment to this and this, you get that. Right? So that's the essence of a proof. You're doing the hard work, you're doing the creative work, and then you're spelling it out for the reader, so the reader can just sort of go through and nod their head and say, yep, I guess it's all true. All right. And then you said if P or T is true and P is false, T has to be true. And that is correct. So the way that we're going to write that formally, first we're going to write P or T. And that's a hypothesis. And then we have a rule of inference, which says P or Q and not P implies Q. So if we know that the disjunction is true and we know that the first thing is false, the second thing has to be true. And if we happen to know, the disjunction is true and the second thing is false, then the first thing has to be true. So this combined with this lets us conclude that T is true. And that's disjunctive simplification using statement 5 and statement 4. So we've just proven that T is true, and that's the thing that we were trying to prove. So that's the end of our proof, and we indicated by saying T is the thing we were trying to demonstrate. Right? And so here this actually means, T is what we were asked to show. And I wouldn't write QED right here unless the purpose of the proof was to prove P or T. If we were trying to prove P or T, we could put QED right there, but we're asked to prove T, so the last line of the proof had better be T. And then we can say, by the way, that's what we were trying to show. It's Latin for which is what we were asked to demonstrate. And that marks the end of the proof.
So with the nomenclature for disjunctive simplification, is it, I guess, proper to put 5-4, or would 4-5 be okay as well for the...
I would not ding you for either, but I wrote 5-4 because the way that this rule is written is given a disjunction and the negation of one term, we can conclude the other.
Yeah.
And so to apply this, if I really didn't want the reader to have to think, I'd want to hand them, this thing first and then that thing. And so the disjunction was, 5 and the negation was 4. But, it's just a matter of using commutivity to come up with a different version of this, which says not P and P or Q gives you Q. But since I'm holding their hand anyway, I figured I'd go all the way and be super hand-holdy about it. And the reader is me, right? And obviously, if you skip a step, I can probably figure out what you did, because I've assigned the problems and I've gone over these steps and so on. And so if you went, straight from here to here, I would probably be able to figure out that's what you did, right? But technically, it would not be a complete proof, right? To be a complete proof, it's got to be a presentation that somebody who understands, what these terms mean and what these symbols mean could conclude the same thing that you did without having to figure out the proof themselves. So it's this very, very spelled out exposition of how you get from here to there. And again, it's not always clear. We've done a couple of these now, and sometimes you just try things at random, and sometimes that gets you somewhere. Sometimes it gets you a mess. And sometimes you see things like, oh, these two could get chained together, or if I did contrapositive, I'd get another not Q, and maybe I could put that together with something. But the more you do these, right, the better your intuition becomes. And so you've got some problems from the homework to work on. So some of these questions from section 3.5, I've got you working on question 4, which is, direct and indirect proofs of these. We'll talk about indirect proofs in a bit. But these questions all have answers in the back, all the odd questions. And so there's 5 more questions you can work on. And in the chapter itself, it talks about some examples of proving different theorems, right? And you can work through those and so on. So don't just do the assigned questions and, you know, get a few of them done and hope you get partial credit, right? Try to work on these enough that you start to feel confident that, you know, given a different question, like on a midterm, you could you know, come up with some way to approach the proof. All right, so these are called direct proofs. They're direct because we begin with the things that we know, the hypotheses that we know are true, and we apply these rules until we conclude the thing that we're trying to show. There's a different method of proof called an indirect proof. And an indirect proof feels very different. An indirect proof, we start off by assuming the thing we want to show is false. And then we do some work to show why that cannot happen. So direct, we start off with what we know is true, and we prove that the conclusion is true. An indirect proof, we assume the conclusion is false, and we work with that, and we find a problem. And once we find a problem, we say, okay, so that conclusion could not have been false, it must be true. And weirdly, sometimes a direct proof works best, sometimes an indirect proof works best. So direct proof, we start with the hypotheses and we work to prove the conclusion. That's what we've done in these last few examples. An indirect proof, we start with assuming the negation of the conclusion, and we work to a contradiction. And the quintessential contradiction is true equals false. And then we say, hey, if this conclusion is false, guess what? True is equal to false. Up is down, left is right, the world is broken. So this conclusion can't be false, it must be true. It's this kind of backhanded way of proving something by saying, if this is not true, really bad things happen. Everything breaks. So let's look at an indirect proof of this same question. So let's prove not Q, P implies Q, P or T, therefore T. Okay, step 1, I'm going to assume the conclusion is wrong. So my reason for this is the negation of the conclusion. I'm going to assume this is a true statement, not T. In other words, I'm going to assume T is false. And using that and my hypotheses and my rules of inference, I'm going to argue to something ridiculous. And since ridiculous things can't happen in this topic, we're going to have to conclude that this was incorrect. Not T is false, and so T must be true. So I know that P or T is true. That's a hypothesis. And I can combine that with not T to conclude P. Right? That's another example of disjunctive simplification using 2 and 1. Well, I also know that P implies Q. That's a hypothesis. And now I'm going to use detachment and put 3 and 4 together, and I'm going to conclude Q. That's detachment using 4 and 3. But I also know not Q. That's a hypothesis. Okay, at this point I can see a contradiction. I've proven Q and I've also proven not Q. And both of those can't be true. So at this point I would be fine with saying contradiction. But if I wanted to be a little more explicit, I could add another step here. Right? Everything that we've written in this proof is true, which means that both of these statements are true. So I know that Q and not Q is also true. Right? And that's just restating what I proved in steps 5 and 6. But we have an identity, and I think it's on page 58, which says P and not P is equivalent to 0. That's the negation law. Well, we've just shown Q and not Q is true. That's equivalent to false. That's the negation law. And now we have, you know, the quintessential contradiction. We just proved false is true. And that's the classic absurdity. So I'm going to write the symbol like this. And this means, you know, contradiction. And I'll, you know, mention it's statement 8 that's the contradiction, right? Because false can't be true. All right, therefore, and the 3 dots mean, you know, therefore. Therefore, this original thing must be wrong. Negating T led us to an absurdity, therefore T must be true. And then here again I'll say QED, because T is the thing that we were trying to show. So that's an indirect proof of T. And it used, you know, some of the same things that we used in our direct proof, but in a very different way. And usually for these proofs, there's one approach that's going to feel a little easier than the other. Sometimes for our proofs, it's almost impossible to do it one way, and it's very easy, or relatively easy, to do it the other. So for the homework, you're asked to use both, but sometimes you're given the freedom to choose how you want to approach a proof. And, you know, you try a direct proof, and if that doesn't feel like it's working, you can try an indirect proof, and so on. All right, so some details, right? I'd be fine after step 6 with saying contradiction and just naming 5 and 6, because Q and not Q, that's a pretty straightforward contradiction. But I wouldn't stop too early, right? I wouldn't stop here and say we've got a contradiction, because Q is not a contradiction, right? Q, none of these things taken together is a contradiction. It's only a contradiction which I also mention not Q along with Q. Now that I've got both of these as my part of my proof, I've got a contradiction. And I would not say QED right here, because QED would mean I was trying to prove not Q. Well, that's not what I was trying to prove. I'm trying to prove T. You only get to say QED after you've written down the thing you're trying to show. So I've got a contradiction here. Let me say there's a contradiction, and then at that point, let me say, therefore, this original thing I negated must actually be true. So T must be true, and then I can say QED. And a lot of the details about proofs are how you present it. You can get, you know, down to here, and you've done all the hard work, you've done all the tricky, intuitive work of figuring out how to find a path, you know, to a contradiction. But you still gotta take the reader the rest of the way there. You gotta say, oh, and by the way, not Q is true, and by the way, that's a contradiction, and therefore T must be true, and by the way, that's what we were trying to show. Right? So if you stop here, you've only got about half the proof done. So take the reader all the way to the thing that you were actually asked to show, and then kind of hit them over the head and say, see, there you go, that's what I was trying to prove. Alright, there's another way of viewing an indirect proof, and this may be helpful or it may be overly painful. If it's overly painful, you can ignore it for now. But this may help, because sometimes the indirect proof, the way I've described it, feels kind of like wiggly, like we're just playing games or something. Let me show you what's actually going on. This is really just the contrapositive. So, suppose we're trying to prove A, comma, B, comma, C implies X. So we're trying to prove this thing. Alright, with an indirect proof, we start off with not X, and we do some stuff, and maybe we use A and B and C and some other stuff, and eventually we prove false. Okay, why does that prove that X is true? And I've said, you know, we're assuming X is false and we're finding something absurd, and that's not good. But more formally, here's what's happening. We are actually showing that not X implies false. It's a direct proof of this fact, that if X is false, then, you know, false is true. If this is a true statement, we can conclude false. Well, if we formally have shown this, we've also shown its equivalent contrapositive, which is not false, implies not X. That's the contrapositive. Well, not false is true, and not X is the same as X. So if we show this, we've also shown that true implies X. And we know that true is always true, and so by detachment we can conclude X. So this is logically equivalent to X. And it's basically just using the contrapositive. But the way we usually think of it is, if X is not true, then we get an absurdity, and so X must be true. But this is the sort of formal reason why proving this also proves that X is true. So that's something you can think about, like I say, if it helps. If not, don't worry about it. Alright, let's talk about the counterpose to proofs. Let's talk about fallacies. And fallacies are theorems are things that are true, right? It's a statement that can be shown to be true, and we show it by using a proof. A fallacy is something that in fact is false. It's kind of like an anti-theorem almost. And there's two main fallacies we're going to work with. And I'm going to label this fallacy so we don't accidentally confuse these with rules of inference. You obviously don't want to use a fallacy as part of a proof, because you'll probably end up with an incorrect proof. So two very common fallacies. Here's the first one. And this is not a rule of inference. This is not valid. If P then Q, Q therefore P. And this is called the fallacy of affirming the conclusion. So the argument here is we're told if P then Q, and we're also told Q, and therefore we're going to conclude P. Does not follow logically. It's not a theorem or a law of inference, it's a fallacy. And it's named the fallacy of affirming the conclusion. We have a conditional statement, and we decide the conclusion is true, and then we make this erroneous conclusion, which is that P itself is also true. Alright, I'll give you a classic example. Let P be the proposition you are a bank robber. Let Q be the proposition. You drink water every day. So this is the proposition. If you are a bank robber, then you drink water every day. And assuming people drink water every day, right? This is a true statement. Well, Q is the proposition that you drink water every day, and I'm guessing that's true for most of you, so this is also a true statement. And if you were to conclude from this that P, you could conclude you must be a bank robber. And it's not logically true, because people who aren't bank robbers also drink water every day. So you can't conclude P from these two statements. It's a fallacy. Now, P could be true. You could be a bank robber, or you might not be. Right? But these two statements taken together do not force you to conclude that P is true. Alright, so that's a fallacy. And it's a very common fallacy. It's a fallacy that gets applied by you know, adults and people who make laws and run the country and all kinds of things. It's a logic error. And, you know, it's really close to detachment, which says, you know, P implies Q, and P lets us conclude Q. Well, that's a true theorem. But this is not. So that's the fallacy. Go ahead.
Oh, I was just going to say, I feel like this is the conclusion of many studies.
Yeah,
as
yeah.
well.
Totally.
They find correlation, but it's not causation.
Right.
necessarily.
Exactly. And that's a huge problem. And, you know, this is something that historically people did not realize or, you know, chose to ignore. And it's something that, you know, a lot of times today we still see this kind of mislogic being applied. And unfortunately, if you try to tell somebody, well, that's the fallacy of affirming the conclusion, they're probably not going to be convinced unless you send them to take CSE215. But it's good to know at least, you know, where you stand. All right, so here's the other fallacy, and this is closely related. So, if P, then Q, not P, therefore not Q. And that's the fallacy of denying the hypothesis. So you have a conditional and you deny the hypothesis, you say the hypothesis is false, and then you draw an incorrect conclusion. And so same pair of propositions. P is the proposition you're a bank robber. Q is the proposition you drink water every day. If you are a bank robber, then you drink water every day. That is true. You are not a bank robber. I'm assuming that's true. Therefore, you don't drink water every day. Well, that is not a valid conclusion. Most likely you do drink water every day. So this does not follow from those. And so be careful when you're doing proofs that you don't accidentally use one of these fallacies, because it's a very quick path to an invalid proof. And you can prove all kinds of wacky things if you use fallacies like this. All right, let's do some examples. Let's have some fun with this. We'll get away from the disjunctive simplification and all of that stuff, and we'll just play around with this in sort of plain speak, just to work with the mechanics of it. So let's talk about even and odd numbers. And let me give you a definition. We're just going to work with integers here, so I'm not going to keep saying, you know, integer, integer, integer. Just fix integers in your mind for the rest of today. So I will say integer, because I can't not. An integer n is even if there exists an integer k such that n equals 2 times k. That's a good definition of an even number. Basically says an even number is twice some other integer, some whole number. N is odd if there exists some integer k such that n equals 2k plus 1. In other words, a number is odd if it's one more than twice an integer. And we're going to use these definitions a lot. We'll do a lot of questions on evens, odds. You'll get some homework questions on those. You'll get some exam questions on those. So we'll use these definitions again and again. So for example, why is 20 an even number? 20 is even because there exists an integer 10 such that 20 is 2 times 10. 21 is odd because there exists an integer 10 again such that 21 is 2 times 10 plus 1, one more than a multiple of 2. So let's prove if n is even, then n squared is even. And if you think about it, this is believable. 2 is even, 2 squared is 4, that's also even. 10 is even, 10 squared is 100, that's also even. Negative 6 is even, because it's 2 times negative 3. Negative 6 squared is 36, that's also even. So this seems, plausible. I tested it on 3 numbers. So how do we prove this? Well, this is an if-then statement. It's basically if this, then that. So how do we prove this implies that? First we assume this, and then we do stuff and try to show that this is true. So my first statement is just going to be n is even, and the reason for that is hypothesis. And if I don't assume that, there's no way I can show n squared is even. So I got to know something about n. The only thing I know is n is even. So that's the first statement of my proof. And there's almost nothing I can write after that. I can't really say anything else about n except for one thing. I can say that since n is even, there exists an integer k such that n equals 2k. And that's kind of the only thing that I can do from here. So let me say there exists an integer k such that n equals 2k. And why is that true? That's the definition of even. Well, what could I try doing from here? Even if we don't know if it's going to help, what could we do after this?
We could rewrite the definition of odd.
We could rewrite the definition of odd.
It won't help.
If we had an odd number kicking around, I would definitely do that. What else could we try? Like I say, even if it doesn't seem like it's going to lead us anywhere, should we multiply n by 100, or
Multiply n by n.
yeah, let's multiply n by n. Why? I don't know, but we got an n squared we got to do something with. Let's just write down what n squared is. And guess what? We've got a new way of writing n. We can write n as 2k. Let's just plug that in. And let's just say n squared equals 2k squared equals 4k squared.
So arithmetic is valid here?
So arithmetic is valid here, right? And so I'm going to say the reason for this is algebra and what we did in statement 2, proposition 2, which was that n equals 2k. And you got to be a little careful with this. right? Because sometimes I'll get students who will just write down, you know, n squared is even, and the reason is algebra. Well, it's not. That's not a rule of algebra, right? But the fact that we can take 2k squared and write it as, you know, 4 times k squared, you can do that, right? We're not going to force you to prove 1 plus 1 equals 2, or things like that.
So we don't have to prove that algebra is valid.
So you don't have to prove that algebra is valid, yeah. Because that would make your exam a little longer. All right, well, what can we do? We've shown n squared equals 4 times k squared. Any ideas what we can do after that?
Define. Oh, never mind.
So let me show you a trick that I like to do. I like to mark off an area of my proof. That's not very well marked. Mark off an area of my proof and say ignore. And I'm going to do some sort of scratch work over here, because I don't know where to go from here. And I'm going to try some things, I'm going to look at some things differently, and I'm going to hope that I get some insight. But I want to make sure the person reading this doesn't think that these scribblings are part of the proof. This is just me thinking out loud. So I'm going to clearly mark this with ignore, and I'm going to separate it from the rest of my proof. And I'm going to put down some ideas here, like, you know, show n squared is even. And to show that something is even, show that n squared equals 2 times some integer, right? And I'm just thinking aloud. This would not be a valid part of a proof, right? But it's in my ignore section, so it's okay. And now I'm thinking I want to show n squared can be written as 2 times some integer. And if I look over here, I've got n squared written as 4 times some integer squared. Can I show that this is equal to 2 times some integer? Can I write 4 as 2 times some integer?
Yeah.
Yeah, 4 is just 2 times 2, right?
Right.
So I could say this is equal to 2 times k squared, which is equal to 2 times 2k squared. And this is more, you know, algebra.
And because 2k squared is an integer, therefore you go back up to n equals 2k is even,
Mm-hmm.
for the definition of even.
Right. So I'm going to say 2k squared is an integer. We haven't proven that, but here I'm going to use another thing we can do in here, which is called properties of integers. Again, be a little careful, right? The square of an even is even. That is not a property of an integer. But a property of an integer is that if you multiply 2 integers, you get an integer. If you square an integer, you get an integer. If you add 2 integers, you get an integer. These are things we call closure. When you do stuff with integers other than dividing them, you get another integer. So if I take k, multiply by 2, since k is an integer, this is going to be an integer. And so now I can say, therefore, n squared is even. Because I just showed n squared is equal to 2 times an integer. So this follows from statements 3 and 4 and the definition of even. And that's where I can say QED. That's what I was trying to show. N squared is even.
Beautiful.
Yay. Alright, we got 5 minutes left. I haven't left you with a Freaky Friday for a while, so let me leave you with a Freaky Friday. So let's prove that the square root of 2 is irrational. And this is the theorem that the Greeks discovered and they didn't tell anybody about, because it destroyed it raised questions about their idea that integers and ratios of integers, fractions, could describe the entire universe. Because if you took a little 1 by 1 square and you tried to find a fraction that corresponded to this length, you couldn't do it. Right? This length is what we call the square root of 2, Pythagorean theorem. And what is this equal to? Well, it's approximately 141 over 100. But the Greeks wanted to know exactly what pair of numbers can you divide to find the length of this. And they eventually stumbled across the fact that there was no such pair of integers. There was no fraction of integers that gave you this exact length. And they got all hush-hush on that fact, and they forbid the members of his cult from talking about it. And this is the one where some guy went out in town and started telling people about it, and so the other people took him out for a boat ride and pushed him off. So this was, you know, forbidden knowledge. He swam back to the shore, actually, even though he was like in his 80s, I think. So let's prove that the square root of 2 is irrational. So we're going to do a proof by contradiction. And this is, you know, the last 4 minutes of class. So this is not on the test, but this is just for fun, right? So let's do a proof by contradiction. So assume square root of 2 equals p over q. P and q are integers. And let me make one other assumption. P and q have no common factors. In other words, this is a fraction in simplest form. So if it's, you know, 15 over 3, we would change it to 5 over 1. Or if both of these were even, we would divide them by 2. So we're assuming square root of 2 is p over q. Alright, so square root of 2 equals p over q. So let me square both sides. And 2 will be equal to p squared over q squared, which means p squared equals 2q squared. And I'm just going to write this across because we're almost out of time. P squared equals 2 times q squared. Well, 2 times q squared is going to be an integer times 2. This is going to be even, which means this is even. And we'll prove later on that if p squared is even, p is also even. We can do that with an indirect proof. We'll do that on Monday. So square root of 2 is p over q. 2 is p squared over q squared. P squared is equal to 2q squared. This is even, so p squared is even. Therefore, p is even. So whatever this magic fraction is, the number on top is a multiple of 2. Alright, so let's write p equals 2 times x, since it's twice an integer, right? And so we're assuming x is an integer here. And so p squared equals 4 times x squared. And that's equal to 2q squared. Divide both sides by 2. 2x squared equals q squared. This is even. And so q squared is also even. And since q squared is even, q is even. And so we've just proven that p and q are both divisible by 2, and that violates our assumption that p and q had no common factors and the square root of 2 was equal to p over q. And so the conclusion is that the square root of 2 cannot be written as p over q. So the square root of 2 is irrational. Can't be written as a fraction. And that's, you know, a pretty simple, but I think horribly clever proof that leads you to this crazy realization that, like, this simple idea of the diagonal of a 1 by 1 square has a length that can't be written as a fraction of integers. And that kind of blew the mind of Pythagoras and his friends. All right, so so Monday we will talk about homework questions if you have them. We'll work through some more proofs about even and odds. We'll do an indirect proof that if p squared is even, p is even. and we'll do some similar proofs for odds, and we'll play around with this a little more, and then we'll go on from there to a new unit, which is number theory, before coming back to proofs. So my suggestion, take a look at the homework, and come by office hours tomorrow if you have questions about it. Otherwise, have a great weekend, and I will see you on Monday. All right, thank you.
Have a good day.
Thanks, you too.